Hi, it's time for another math easy solution. Turn to discuss further into approximate integration, and now look at the Simpson's rule error bound and go over a proof for it. Yeah, so this proof is pretty extensive, and it's not shown in pretty much any textbook I've seen, but luckily I found the proof for it. So basically the error bound for Simpson's rule is right here. Suppose that the absolute value of the fourth derivative of x is less than or equal to a number k for x is between, x is greater than or equal to a, less than or equal to b. Then the error is when you use the Simpson's rule, and I'll go over Simpson's rule again. It's basically absolute value of this error is less than k times b minus a power of 5, all divided by 180. And now we'll go over the proof, but first let's recall the definition of the Simpson's rule, which I went over in my previous video, so make sure to watch that. So if you had, let's say, an xy curve like this, and you had a function that shows that's something like that, and let's say at this point here, this is a, and this at here is our b, and we want to approximate this function f of x. Then the idea of the Simpson's rule is basically to break this up into many subintervals, but an even number. So we'll do like that and keep going, etc., all the way until we get, let's say, up to here. So this is going to be, our x0, this is our x1, x2, all the way up to here. This is going to be equal to, xn. So it's n sub-intervals. This is right here is our xn minus 1. That's our xn minus 2. And again, the idea of the Simpson's rule is to draw a parabola for basically even number of sub-intervals, and then you go every 2. So you would draw basically a parabola that cuts through both of these points. So you'd basically have a bunch of parabolas like this. And then you would keep going, etc. So you'd have a point here, another one like this. So basically every 3 points you're going to have a parabola approximated, and again you're going to have it like this. And you're approximating it using parabolas, and this is going to be, we'll call this Sn. And again, I'll write that down. These are all parabolas every 2 subintervals. Parabolas. Yeah, like this, and over here, so basically each one of these distance between here, this is delta x, and this equals to, b minus a, the full length, divided by the total number of subintervals, n. Yeah, and again, recall from my previous video that the Simpson's rule approximation is thus when you go over, when you find the parabolas, formulas for the parabolas, you get something like this, where the integral from a to b of f of x, f of x right here is roughly equal to, approximately equal to delta x divided by 3, and then times it by, you have now f of x0 plus 4 f of x1 plus 2 f of x2 plus 4, and then there's 2 again. It goes 4, 2, 4, 2, etc., all the way, and then we have a 1 at the end, and beginning there's a 1 in the coefficient. So this is a 1. There is a 1 right there, and it goes to 4 xn minus 1 xn. So that's the pattern. You can see in my earlier video how I derived that. And again, n is even because we're going every 2 subintervals. So again, this point right here, that's 2 delta x. So we need to have even if we're doing every 2. Yeah, and basically the error using the Simpson's rule is just like all the other errors that I went over to the trapezoid and midpoint rule. What we have is the exact integral from a to b of f of x dx. This equals to, our approximation Sn plus, and then we go Es right here. And now we just rearrange this to solve for Es. So Es equals to Sn minus, actually, whoops, not that. I mean the other way around. So you have integral of a to b f of x dx minus s of n. Yeah, so basically we have the exact integral minus the approximation, and that's just basic error. Yeah, and now in deriving the proof of the error bound, let's first derive the error bound associated with just 2 subintervals, and then later we'll go through and sum up all the way from a to b. And again, we're using 2 subintervals because Simpson's rule requires 3 points to get the parabola. So we go, if we were to draw it out, let's say we have a function like this. This is the subinterval part of it. And in this case, we'll just use A right here. So this is the point A. And then at the midpoint here, we'll call it C. And then here, this is our B. So A, B, and then the C is the midpoint. This is our f of x. And again, our S, or our approximation is a parabola. Let's say something like this. And this could be our S. Yes, we'll just call that S for Simpson's rule approximation. And that's the highlighted here under the red. So again, you're going to have an error here. It's too low here, too high over there, etc. Now, this is the part of the proof that's pretty complex, and this is the only proof that I was able to find. So now, basically, in proving the error bound, let's first define the following function and integrate by parts, by integration by parts, 4 times, because we are dealing with a 4th derivative. So this is a pretty unique way of solving these kind of error bound solutions. So it's kind of like working backwards. So we go define integral from a to b of f of, this is the 4th derivative of x, and then p times it by p of x dx, where in this case p of x is a monocortic polynomial, and I'll explain what that is right now. Yeah, now basically note that a monocortic polynomial simply means that a polynomial of the 4th degree, so the power of 4, and a polynomial, again, you can see my earlier videos on that in the video link below, where the coefficient of the highest degree is 1. For example, this function right here, I'll just write monocortic, is of the form like this. Let's say x4, so the initial one is mono, so there's only a 1 here, so the coefficient is 1. Just delete, I'll just remove it, so it's nothing in front. And then again, plus a1 x3 b, we'll call this a2 actually, a2 x2 plus a3 x1 and then a4. Yeah, something like that, or usually actually a better way of defining the coefficients is we'll go a0 here, and it doesn't matter here, this is a1, it's just for neatness. Like that, and then our a4, in this case, this equals to 1. So that's all that this monocortic means. Yeah, and this, the way we're defining it will come in handy soon. And now what we do is basically integrate the function above right here of 4 times by the method of integration by parts. And again, recall the integration by parts method. Yes, if we recall it from our earlier videos, it's basically u dv, integral of u dv equals to uv minus, and then we have we just switch around, v du. This is going to be du. So now in our case, so that's what we have right now. What we're dealing with is the integral from a to b of f4x and then p of x dx. So what we want to do is work backwards. So this is the 4th derivative. We want to eventually get to f of x, so without a derivative. So we want to get to that. To do that, we'll have to work backwards. So what we'll do is let, in this case, so this is u becomes du, so but here dv becomes v, so that's an integral. An integral will make it closer to, if we do a 4th derivative, we want to get to the 3rd derivative. So what we do is define u as, because we're going to do the derivative, u as p of x. So that the du in this case is going to be p prime of x dx. And again, we're doing that so that then the integral that we're left with has a derivative of p, but an integral of f of x right there. So in this case, dv, we're going to define dv as, dv in this case is going to equal to, well, f 4th derivative of x and then dx. That's including this part right here, so that when you take the integral right here, this becomes f of 3x. And now we could throw this back into this little integration by parts formula. And as you can see, what we get is something like this integral. So now from a to b of f of 4x px dx equals to now px. This is our u. This is our v right here. That's our f of 3 of x. And again, this v goes here, and this becomes our du right there. And again, now we're doing from integral from a to b. So now this is from a to b, and this is integral from a to b. And now what we do is do integration by parts again. So we write that by parts again. And what we get now, it's exactly the same thing. We let u now equals to the derivative of x, and then du is just going to be, well, the second derivative of p of x, like that, dx. And again, our dv equals to this right here, the third derivative of f of x. And then the integral is going to be, well, the second derivative of f of x. Like that. And then again, we throw that in. Yeah, I'm throwing it in. I'm including this negative sign just so that at the end we just add everything up with positive signs, or that we don't need to flip around the signs. So when we do that, this negative goes into here. This becomes, and again, this because there's a negative, the integration by parts will have a negative, then a positive, like that. Then again, this is our v, this is our u, this is our v, and this is our du right here. And again, we do by parts again. Yeah, so I'll write that down again, by parts again. And then what we get now again is the same thing. U is going to be equal to our second derivative of p of x. And then our du is going to be equal to the third derivative right there, dx. And then our u, our v right here, we have our dv is equal to f second derivative p of x, and then our v is going to be equal to the first derivative of f of x. And again, throw that in. Yeah, and when you throw it in, you get, well, this function right here, where this is our v, is our first derivative of f of x. This is going to be our u, the second derivative of p of x. And then this part right here, this is again our v, and then this is our dv, the third derivative of p of x. So again, we do this by parts again. So we keep going one last time. But in this case, this is going to be something pretty interesting. So what we have right here, our u, will define it as the third derivative of p of x, and then du is going to be equal to the fourth derivative, like this. Yeah, like this, d of x, and then our dv, again, that's going to be equal to f prime of x dx, and then the integral v equals to, well, f of x. So now we have our function f of x that's finally shown, but now we have this fourth derivative. But now the reason we chose a monocortic function as p of x is because, well, we could solve for the fourth derivative. So basically recall that it's a monocortic. So let's say we had this function if p of x is something like this, x4 plus a3 x, we'll call this 3 plus a squared x, a2 x squared plus a1 x to the power of 1, and plus a 0. And now, since this is a monocortic, the first value is a 1, we could basically solve for the fourth derivative. So this is why we define it like this. The first derivative, p prime of x is equals to, well, let's solve this derivative. This is 4x3 plus, this is going to be 3a3 x squared plus, this is 2a2x, and then this part right here is plus a1. This goes to 0. And see, now you get the idea. Now the second time we'll do this, this 3 goes down, so we'll have a 12x squared. This is going to be 6a3x, and the last one's 2a2. So now we've got rid of two coefficients, a0, a1, because this one's going to be 0, and now we do it the third time. This is going to be, well, 24x. This is going to be 6a3, and then the last time, the fourth derivative, this just equals to 24. Yeah, thus what we have is our du above p4x this just equals to 24 dx. So that's all it is. So now we don't have this p of x inside that formula anymore. And again, now when we put this over here, and again there's a negative sign because in this case we take out this whole negative out just to make it easier. So negative, then there's be a plus, and this is going to be our, that's our v. This is our u. And then our, again, there's a 24 there. So this is going to be our du. I mean, not du. This is going to be just our v. Yeah, I'll scroll up. That's our v. So f of x is our v, and our du is going to be, well, 24. Yeah, that's just our du right there, 24, and dx. We just take the 24 out. And now when we put all of this together, would we have integral from a to b of fourth derivative of f of x px dx equals to, now what we have is basically see the pattern. This is the third derivative of f of x times p of x from a to b, then minus the second derivative of x, then the first derivative of p of x. So this derivative keeps going down, and then this keeps going up, and the signs go from positive, negative, positive, negative, exactly as we were shown above. So initially, if we go all the way back up, the very first one, the sign is positive, and there's a minus, so there's a minus right here, and then we have a positive, then we have a minus, and the last one is positive. So that's exactly what we have. This derivative keeps going down for f of x, but for p of x keeps going up all the way till we have this 24 integral from a to b of f of x dx. Yeah, but since the Simpson's rule has values at 3 points, endpoints a and b, as well as the midpoint c, we can evaluate terms from a to c and from c to b. And what we get is right here, integral from a to b of fourth derivative of f of x px dx equals to, well, this is the first point from a to c, and then from c to b, and then minus from a to c of this second derivative, first derivative p of x, etc. And again here, so the second derivative, first derivative, and then from a to c, c to b. And then it's basically exactly the same thing as this above, but we broke it up into, yeah, from a to b. Yeah, we broke it up from a to c and then c to b, and that's the same thing as over here. But we left this integral. Notice that we just left this 24 a to b of fx dx because that's the integral we are trying to approximate. And then when we start evaluating all this, we get this, and I already had this typed out because if I were to write this out, the video would just be, you know, couple hours long. So what we have, we evaluate it, and notice here the c minus, this just means from the left side of c or the midpoint, and then this one, this c plus, that is from the right side of c. So c plus right side or right of c. Because if, as you see, if we have this A, and then this is B, and then C, so since we have since we're evaluating from A to C, so then at this point here, this is going to be our C minus, so from A to C minus, then we have it from, at this point right here, C plus, so we go from C plus to B. So that is what I'm trying to say right here. Because, yeah, there is no one value C when we plug in this P of C. So we have to consider the left side and the right side. So again, all I did was just plug these in. So we plug this C inside, P of C minus, and again this. Yeah, but for the F of F triple prime of C, we just assume that is continuous. Yeah, and here's basically another note that I forgot to mention earlier, is that p, the function p, is required to be continuous from, well, a to b for up to the second derivative of p of x. And we'll prove this this is actually the case soon, but for now we'll just use this left side of c and right side of c, and we'll show that it is equal for the up to the second derivative. And the function f of x is assumed to be continuous, and thus don't need to deal with, well, the left side and right side of c. So when we plug these in, as you could see all the way here, c, then we minus a, then we have b minus the c from the right side, then we have the c from the left side. Basically, if you just keep going through all of these, it's really tedious, so I'm not going to dwell too long into that. And then the next part of it is to simplify and group the terms with c together. And when we do this, we get something like this. So we put this negative f triple prime f third derivative of f of a, that times p of a. That is this part right here. So we move it to the left, group all of the, take out this f triple prime of c out of the ones with the c. So we take that out. So we take this out. So we're left with something like this, p c minus c to the left side minus c to the right side. So that's this first part. This one, put it separate. That's this. And then this is again, what we're kind of trying to do is write it that looks kind of like the Simpson's rule in some way. Yeah, so we have this is the first endpoint, this last endpoint, this is the third derivative. And then when you go to the second derivative, it's the same exact thing. So basically it's all the same thing, just really tedious, and it just looks like it's a lot, but it's pretty simplified. And again, the pattern is this derivatives go down for f, go up for p, and then we have, in every single case, we have this subtraction of the c from the left side and c from the right side. And later we'll show these are equal, so these just cancel all out, all the way to this third derivative, etc. And then this, we just left this 24, a integral from a to b of fx dx. And again, the signs alternate, it's plus minus, so make sure to keep track of that. Yeah, now when we're trying to derive the error-bound rule, we don't want any evaluations to have the derivatives of f. So we want to try to impose that, so these derivatives are not there, so we try to impose this to equal to 0, and then also that this goes to 0. What else? This goes to 0. So this is what we want to impose. This goes to 0. Ignore the c's for now, because remember, those are supposed to be equal. And then this part right here goes to 0. And then this part right here, where is it? Yeah, this goes to 0. This goes to, yeah, that goes 0. And then these ones, f triple prime, we don't need to make it go to 0, because that's just dealing with regular f of a. So what we're trying to say is we have to make 0 equal to p of a, that's this one, equals to, well, the first derivative of p of a, that is over here, that's the 0, and then this equals to p of a as well. So we have to impose that this all equals to 0, and also for the p of b side. P prime of b, that's up to here, and then over here. So we're trying to get rid of all of the derivatives of f of x. That's p of b. Yeah, now we know that p of x is simply a monochordic polynomial, and accounting for the midpoint c as well as the conditions shown above here. So we want to make this true for our case. So what we'll do is we'll define p such that that it follows all of the clauses that we pointed out. So it's going to be a piecewise function where we have x minus a cubed times it by x plus d1. So that's a coefficient. This is for a is less than x less than c. And this is x minus b right here. X plus d2, the coefficient. And this is for c is less than x less than b. So we broke it up into two parts, and again, this is a monochordic. If you multiply this out, there's an x, you'll have an x cubed, and you'll have an x right here. So when you multiply it out, that's x to the power of 4. So we're defining this basically to match up all our what we want for the function. And then we just need to solve for that coefficient to make it fit all nicely. So when we do this one right here, x power of a power of 3. So when we plug in a, we have, well, the whole thing goes 0. When you plug in b, goes to 0. And when you take the derivative, you'll be dealing with x squared. And again, when you plug that in, the derivative gets 0. When you do the derivative again, then you'll have an x minus a. So you also have this x minus a around, and then the derivative will go to 0. So this is basically matches up with all of these conditions because this is x because of this power to 3, or this cubed. And again, here the function p of x is defined as being continuous. So yeah, I made another little just typo right here. I'll remove this. We'll prove this soon. We're actually defining this. This is defined, so we do not need to prove it. We're just going to say it is, and then find the d1, d2 coefficients accordingly. So I'll just erase that part. So we have right here p of c minus, left side equals to p of c plus. So we are defining it so that it is this. So this is the case, and we just need to solve for the coefficients to make it match up. So when we set these to equal each other, what this means now is when we plug this inside to, well, the left side, we're going to be plugging into this function, and then the right side we plug into that function. So what that means is when you plug in c, you'll have x minus a, I mean not x, so you'll have c minus a cubed. This is going to be x, I'm going to c again, c plus d1, and then we'll have equals to c minus b cubed, c plus d2. Now a couple things to take note of is that, well, we know that if you have, let's say, an x line like this is 0, this is our x, this is b, this is a, this is our c. So again, this c is the average point across this, and that is basically from here to here. This is just c equals to, well, the average a plus b over 2. So we know this fact, and we also know that this is the midpoint. So it's the midpoint of from a to b. So it's a midpoint from there, so that the distance right here, b minus c, equals to, well, c minus a. So what we have is, yeah, what we have, and also wrote it down earlier, we also know that since c is the midpoint between a and b, it follows that, well, c minus a equals to b minus c. So what I'm going to do in this case is just rearrange this further. So c minus a, so that these kind of line up, equals to, we'll take a negative out, so now we have a c minus b. Yeah, so thus when we put these together, so there's a c minus a, so what we have is, let's go c minus a cubed, this is going to be our c plus d1, and then what we have is equals to, well, c minus b cubed, c plus d2, plug these values in, so this c minus a equals to this right here. Yeah, so what we get is, just plug this inside, we get, this is going to be negative, this is going to be, let's just take this out, negative c minus b, and then we're cubing it, and then we have a c plus d1, and then equals to c minus b cubed, c plus d2. And again, this cube, when you cube this negative, it goes negative times negative times negative, so we're just going to be left with a negative sign that's just taken out. So c minus b cubed, c plus d1 equals to c minus b cubed. This is c plus d2. This cancels, so what we're left with now is negative c, negative c minus, we're just multiplying this negative inside, negative d1 equals to c plus d2. And now what I'm going to do is move this c to the left side, move this to the right side, so we're going to be adding, so we're going to have d1 plus d2 equals 2. Now we have this negative c minus c equals negative 2c, and again recall that the c is just the average, and it's just a plus b divided by 2. So that equals 2, negative 2, a plus b divided by 2. These all cancel, so what we're left with in this case is d1 plus d2 equals to negative a plus b. And this will come in handy later once we try to solve d1 and d2. And now the derivative of p is obtained as follows. Again, because we're trying to solve d1 and d2. So it's obtained as follows for, let's go with a is less than x less than c. So for this case, we have p of x equals 2 equals to x minus a cubed, and then we have x plus d1. So what we do in this case is just use the product rule. So the derivative p prime of x equals 2, put this 3 down, x minus a squared, and then this is going to be x plus d1 plus, now we take derivative of this one. That's just going to be, well, d1. Actually, whoops, not d1. That's just equals to 1. X plus d1, this goes to 0. Derivative of x is just 1, and then we just put this x minus a cubed. And again, what we did is using the product rule. Let's put that down. Product rule. And you can see my earlier video in the video description below, or just search my channel for product rule proof. So we have that. And now this part right here, you could also write this out as x minus a squared times it by x minus a, so that we could take out this x minus a squared. So this equals 2, taking it all out, just factor out the x minus a squared. So now we have 3 x plus d1 like that, and then we are gonna plus this x minus a, so x and then minus a right there. Simplify this out, x minus a squared. This is going to be 3x plus 3d1 minus a, this would be a plus x minus a. So what I'll do right here is add these up, this 4x, so this just, I'll just erase this to make it quicker, 4x minus a. So that is our first derivative. And now I'm not going to reinvent the wheel, and I'll just put down similarly, because it's going to be the exact same thing. Yeah, similarly for when you're dealing with the second part, for c is less than x less than b. Right here we get the exact same thing. Derivative is going to be equal to x minus b now. So the only thing that's different is there's a b, and now there's 4x plus 3d2 instead of the d1 minus, and now instead of minus a, we minus b, because that's all we're doing is just switching the variables. That's all it is. Yeah, and thus when we put it together, we get the first derivative equals 2x minus a squared, 4x plus 3d1 minus a. This is for a to c. Now, and then from c to b, that's just going to be b, and there's a d2. That's the only difference. And again, continuity that we define, p, the derivative of p of x at c requires that p of c minus equals to, or from the left side, equals to p of c plus from the right side. So thus we have, when you plug in c from the top and then the bottom, they have to equal. So we have c minus a squared, 4c plus 3d1 minus a. Then the same thing on the right side, but there's a d2 and there's a b instead of the a's. So we have that, and also recall what we showed before, that c minus a equals to negative c minus b. And that's going all the way up to here. We get here c minus a equals to negative c minus b. So when you scroll back down, so we have this, and also since we're dealing with squared, so we have c minus a squared. This equals to, well, this is the same thing as if we square the other side. This is negative c minus b squared. Doesn't matter what the sign is, you're always going to get a positive value. So this just equals to c minus b squared. So these are both equal. when you square both of them, they're just going to be equal. So what that means, if they're equal, you could just cancel these out. So we are dealing with now is just 4c plus 3d1 minus a equals 2 4c plus 3d2 minus b. And now what we're going to do is cancel this out, the like terms, and we're going to move the move this over to this side, the b, and this 3, we're going to move it over here. So what we get is b minus a equals 2. And then since we move this over, take the 3 out, d2 minus d1. And now we could just find d1 and d2 by solving the two equations. So the first one that we had was, well, negative a plus b equals 2 d1 plus d2. And that's the one that we had. Let me just scroll up to it. That's this one right here. d1 plus d2 is negative a plus b. And so that's what we had. And then the second one is, well, b minus a, this top one, equals 3 d2 minus d1. So first thing we'll do is solve for d1 in this case. So d1 is equal to, just move this over to this side, we get negative d2 minus, take these out, negative a, negative b, and then throw this inside. So what we get now is when we throw this inside and move it over here, we get b minus a equals to 3. Well, actually, I'll divide the 3 out as well. So divide the 3 out, just so we're not dealing with that. So now we have a d2 minus, now there's this d1. Since these are all minus, but there's a minus here, we become all positive. d2 plus a plus b, and now what we're going to do is these add up, d2 plus d2, and also what I'm going to do is make these a fraction of 3. So what I'm going to do is times it by 3, divide it by 3, times it by 3, divide by 3, and then move it over to this side. So what we get now is b minus a is all over 3 minus this 3a minus this 3b equals 2d2. And again, simplifying this, we get this b. There's going to be, well, in this case, what we'll have is negative. In this case, just negative a minus 3a, that's 4a. And then b minus 3b, that's negative 2b. All divided by 3 equals to 2d2. Divide this 2's out, so we're just left, this is going to be a 2 there. So we're left with d2 is equal to negative 2a minus b over 3 equals 2. Take the negative out. This is going to be 2a plus b. Take it over 3. So that's our d right there. I'll just put this like that, or better. Okay. And now solving for our d1. d1, recall this equals 2. Scroll up, d1 is negative d2 minus a minus b. So we have negative. So we have a negative there, so this can be positive. So 2a plus b over 3 minus a minus b. So what we get right here, and again this part right, I'll just write that down. This is our negative d2. So when you do this, again, write the common denominator 3, so multiply and divide by 3, multiply, divide by 3. So this equals 2. I'll go d1 is equal to, take these out, 2a minus 3a, so that's going to be minus a. And then when we have this minus 3b, that equals 2. This is going to be, well, yeah, this is going to be minus 2b. When you subtract 2a minus 3a is negative a, b minus 3b is negative 2b, all divided by 3. This equals to, take this out, a plus 2b over 3. And this is our d2. So there's our d1 and there's our d2. And now continuing forward and solving for the equation p, the second derivative. And again, we're solving for these because of the original formula. Yeah, and when we go back to this original formula, we eventually have this third derivative, which we haven't defined to be equal, and we'll show again later that it's not equal. So we eventually need to solve for the third derivative of p of x. So going all the way back down. And yeah, I just wanted to show that just so we don't get too sidetracked away from what we're trying to do. Yeah, so now for the first part, for a is less than x, less than equal to c, we first write down the first derivative, p of x. This equals to, well, x minus a, like I showed above. Then we had 4x plus 3d1 minus a, and again scroll up to show that. That is, I believe, right here. So that's the first derivative. So for the first part, and now what we're going to do is solve the second derivative, p double prime of x, again using the product rule. So derivative of the first part is going to be 2x minus a, and then we have right here, we just put this here, 3d1 minus a, and then we had plus, this becomes, well, 4x minus a squared. And again, this top part right here, this is just same thing as writing 4x minus a times x minus a. So we're going to factor out the x minus a. So this equals 2, and also take the 2 out as well. So 2x minus a, now we're left with this 4x plus 3d1, let's write this better, minus a, and then since there's a 2 now, we took out that out. This is just going to be minus 2x minus 2a. That's just 2x minus a. And that's like this. And now what we're going to do is plugging in our d1, plugging in d1 equals 2, like I showed, a plus 2b over 3. Scrolling up again. So d1 is a, oh, this is wrong, this is d2, this is d1. So minus a plus 2b over 3. So we have this, plug that inside. What we get is p double prime of x equals to 2x minus a, and now we have a 4x, and then this 3's cancel, so just negative a minus 2b, and then minus a minus 2x minus 2a. And again, simplifying all this, this equals to 2x minus a, and then we have this, actually scrolling back up here, this is a plus x, this is the plus x right there. Yeah, because this is 4x right there when we took out the 2. So now what we have is adding these up, 6x, and then this is going to be, the a is going to be, there's a negative a, negative 2a, so that's negative 4a, and now we do the negative 2b. And now what we get is a part like this, and also take out the 2. I'm going to take out the 2 here, so this becomes a 3, this is a 2, this is a 1, and we put a 4 right here. X minus a, this is going to be 3x minus 2a minus b. And now similarly for the second part, yeah, for x is less than, this is b, greater than equal to c. So for this part, we're just going to skip right to this part that we know it's going to be over here. Let's go all the way up to, yeah, we'll just skip up to this part right here. So I will put that in down here. So this is going to be p double prime of x equals 2. I'll just write that down, 2, and then we're just replacing a with b. And this is 4x, that's going to be 6x, and then there's a 3d1, but that's going to be 3d2. We're just trying to simplify it Because it's the same thing, just different variables. And then this is negative 3a. That's just going to be, well, negative 3b. Yeah, 3b like this. And we stop there because now we're plugging in a different variable right here. So we're going to be plugging in our d2. And our d2 equals 2, this is going to be negative 2a plus b. So the only difference was, yeah, all divided by 3. So the difference between this and the other one is just plus, this is a plus 2b, this is going to be 2a plus b, and that's exactly what we have over here. This is our d2, 2a plus b, and there's a negative sign obviously. So plugging that in, we get p double prime of x equals 2x minus b, 6x, and now we have this right here. This is going to be negative, the 3's cancel, so we'll have 2a minus, because we're throwing that over there, minus b, minus 3b, is this part. So what we have now is equals to 2x minus b, 6x, minus, now this is going to be 2a, and then minus 4b right here. And then take the 2 out, this was 3, this is 1, this is 2, this equals 2, 4, x minus b, 3x minus a minus b. And that is what our p double prime of x equals to for the right side. Whoops, I'm forgetting a 2 right there, 2b. So what we have is this. Yeah, so what we have is the second derivative is 4x x minus a, 3x minus 2a minus b. This is for the left side. The right side, same thing, but there's a b and then there's a 1a negative 2b as opposed to 2a 1b. So now what we're going to do is check the continuity that we defined, that at the up to the second derivative it's equal. So at c at x equals to c from the right side, from the left side, c negative, what we get is p prime of c negative, that's from this side, equals to 4 c minus a, because we're using this is the left side, this is the right side of c, 3c minus 2a minus b equals 2. And again, recall that c equals to a plus b over 2. So putting that in, we get, this is going to be a plus b over 2 minus a, that's this part, and then this is going to be 3a plus b over 2 minus 2a minus b right here. So what we're going to do in this case is, well, obviously here the common denominator times it by 2 divided by 2, and then also we could do is cancel this 2. That's the first thing we'll do. This be just 2. These all cancel, so it would be equal to, this is b, a minus 2a, that's just going to be minus a. So we move that around, and now this part right here, again the common denominator times this is going to be 4 divided by 2, this is going to be 2 divided by 2, this is going to be 3a plus 3b, this is all divided by 2. Oh, and again there's a 2 here, so this is 2 like that, and then that obviously cancels out. So 3b, this is going to be minus 4a minus 2b. So what we get here is b minus a times it by 3a. This is going to be negative a, but this 3b minus 2b, that's just b. This is going to be negative a. So this just equals to b minus a squared. So that equals to the second derivative at c negative from the left side. So now when we look at the right side, at x equals to c plus, is the same thing. We plug this in, p prime of c plus, this equals 2. Now we look at the right side, which is this equation, and that's just gonna be 4, this is c minus b, and then we have 3c, and then there's gonna be minus a minus 2b, so as opposed to 2a minus 1b. So we have that, this equals to now 4a plus b over 2 minus b, I'll just do this quickly, times common denominator, 2 over 2, and then this is going to be again 3a plus 3b over 2, and then this part here, the common denominator, this is going to be 2a over 2 minus 4b over 2. So I just quickly, all these 2's cancel, so this 2's cancel with this, we'll be left with 2, this 2 cancels with all these, so what we'll be left with is 2b, so what we're going to be left with right here is a minus, right here, that's just going to be minus b, so a minus b, and then this part right here is, this part 3a, so minus 2a, that's just going to be a, 3b minus 4b, that's just going to be negative b, so a minus b, this is just going to be a minus b squared. Since we're squaring it, this becomes always positive, so even if you had a negative, this equals to this just equals to, well, b minus a squared. This is square, doesn't matter what you have inside, this is always going to be positive. So this is the exact same thing. Thus what we have is a continuity up to the second derivative, p c minus equals to p c plus. So we defined it, and it was in fact true. And actually, going back to here, we should actually keep this note that I put. So we will in fact see that this is the case, which is so what I deleted earlier. So actually we did just show that it is, and we defined it, and it was true in our case for the coefficients d1 and t2 that we were able to derive. Thus we've just showed p is continuous up to its second derivative, and it exists for all values in the domain from x equals a to x equals b, and this can also be written as, we could write it as b is element of with this symbol c squared, so derivative up to the second derivative of now, this is from the range, the domain a to b, and this is closed brackets, meaning including x equals a and x equals b. And now the third derivative is simply found as, well, for the first case, a is less than x less than c, and, well, first we know that the second derivative is equal to 4x minus a, this is 3x minus 2a minus b. So then this is basically, let's just go back up, that's just this one, 3x minus 2a minus b, so there's the 4 in front. So now the third derivative is going to be equal to, using the product rule again, this is just 4, derivative of x minus a is that, then 3x minus 2a minus b, and then plus 4x minus a, and then derivative of this, that's just going to be times by 3. Or I'll just take this out, that's just going to be, well, 3, that's just 12. Put the 12 in front. So what we get here is, just simplify this out, 12x minus 8a minus 4b plus 12x minus 12. So we get here is, 12a right here. So what we get now, is this 12x plus 12x, that equals to 24x. This is negative 8a minus 12a, that's 20a. And then we have a 4b. And then this just takes, we could take the 4 out. This just becomes now, and we take the 4 out, this just becomes 6x minus 5a, and then minus b. Like that. So that is the third derivative. And similarly, I'll just do this, similarly for for c is less than equal to x, less than equal to b. In this case, the only thing that's going to change is when you go look back up here, there's a 2a, that's a b. The only difference is going to be, well, this is going to be a b, this is going to be 1a, and negative 1a, this 2b. So all that's going to happen is whatever the coefficient is in front of a is going to be the same but for b, and vice versa. So similarly, and I don't want to write it over again, you could do it yourself, but you will get, I guess if you just look at it, it's the same thing, but the a and b coefficients were different, so they'll be different in this final result. So 6x minus what we'll get here, 5a, instead we will get just a, and then minus 5b. So just following the pattern is that's what we get. Yeah, thus for the third derivative, we have this right here, triple prime of x is 4 times 6x minus 5a minus b. For the x is greater than a, less than c, and then for 6x minus a minus 5b for between c and b. And now we could solve for values of the third derivative at x equals a, at x equals to this c from the left side, c from the right side, and b. Yes, so first of all, let's go to the left side, from x equals to a. So at x equals to a, if we just plug that in, we get the third derivative, a equals to 4, plug into the top equation, 6a minus 5a minus b, this equals 2, that is just going to be 4, and this is going to be a minus b. And I'm just going to write it in terms of b minus a, because that's what we're just used to. So this equals to negative 4b minus a, and this will come in handy later on. And now at x equals to c minus, we have p triple prime of c minus, this equals to, well, I'll just plug in c to the top equation. So that's 4, 6c minus 5a minus b, and again recall that c is the average of a and b, so this is 4, and this is going to be 6a plus b over 2, and again 5a minus 5b, and 5b, I'm just minus b, find the common denominator, 2 right here, times by 2 divided by 2, times by 2, which is 10 divided by 2. So what we get here is, this is going to be, this is 6a plus 6b. And also this 2's, we can just cancel all out. We'll have a 2 in front. So 6a minus 10a is going to be negative 4a. And now we have 6b, when you multiply it in, minus 2b equals 2, 4b. So this just equals to negative 8a plus 4b, and plus 8b. And take the b, take the 8 out, move these around, we'll have 8b minus a, so right like that. And now what we do is look at x from the right side, c from the right side. At x equals c plus, we have pc plus equals to 4, and now we're just plugging into this equation where there's a 1a, 5b, like that. So we have it as 6c minus a minus 5b. And again, this equals to 4, 6a plus 6b over 2 minus a, put the common denominator, 2 over 2, minus 10b over 2. Using the common denominator, this 2's all cancel. This cancels with this, we get a 2. So we get a 2, 6a minus 2a, that's just going to be 4a. And then we have 6b minus 10b, that is negative 4b. So this equals 2, and moving these around, this just becomes 8a minus, I'll just take the 4 out instead, so we'll have 8a minus b. So we want in the terms of b minus a, so this equals to negative 8b minus a. And which this equals to, well, negative this is going to be p of c minus, so negative of the left side. And now the last one is at x equals to, let's write this better, at x equals to b, we have b triple prime of b equals to, scroll up, that's this one, 6x minus a minus 5b, this equals to 4, 6b minus a minus 5b, this equals 2, 6b minus 5b, that's just b, so this is equals to 4b minus a. And now if we recall the previous equation from above, I just copied and pasted here, that big giant one right here. And now if we remove all of the zeros as well as account for the continuity at x equals c up to the second derivative, what we get is, well, p of a is 0. This is, what else is 0? This is continuity, so this is all 0. P of b is 0. P prime of a is 0. This continuity is 0. This is a 0. What is pretty much everything is a 0. A lot of stuff is 0. Up just to here, 0. The only thing not 0 is this is not 0. These are not 0. So we've got pretty much rid of everything. Now we're just left with this right here with the third derivative of p of x. And then we have this part right here. And now if we plug in the values that we solved for the third derivative, so at a we had, well, what was a? A's was negative 4b minus a. And that's this right here. So negative 4b minus a times fa, fc. So now this part right here, the first one is 8b minus a. And then the second part here is negative 8b minus a. So when we're minusing it from it, then we'll have a negative 16. And then the next part here, minus f of b, that's just going to be, f of b is just 4b minus a, f of b. So then plus 24, this 24 integral from a to b of f of x. And then now if we simplify further by factoring out this negative 4 times it by b minus a, we get this f of a plus 4 f of c, f of b, plus 24 integral from a to b of f of x dx. And now what do we do if we rearrange and solve, well, basically for the integral of f of x, so that's this part right here. So rearrange and solve it, so move everything over to the left side, and we'll have this plus, we'll have plus 4b minus a, but also now we're going to divide by this 24. When we divide by this 24, that's just going to be, well, divided by 6. So we'll have these all over. So 4 over 24, that equals to, well, 1 over 6. So that's how we got this 1 over 6 here. So these all become, this becomes positive. So we move it over. So now what we have in divided by 24. So we have, this is our function right here. As you can see, this is the Simpson's rule approximation. That's our Sn. I mean I'll just call it our S, our Simpson's rule approximation. And this one could be considered our error. I'll call this E of S, or ES on top. And like I just said, note that the first part of the above equation is a Simpson's rule approximation, and thus the second integral can be considered as the error. Thus we have integral from a to b of f of x dx equals to b minus a divided by 6 times by f of a plus 4 f of c, then plus 4 f of b, and then plus over here e to the, this is Simpson's rule error, where e of s is just this integral of the fourth derivative times p of x, where p of x is equal to this function that we defined, where the d1, d2 coefficients are this accordingly, which we derive. So thus the absolute value of the error is this absolute value of this error, and then put this absolute value sign, and that's going to be less than or equal to k over 24 integral from a to b. And this is less than because we put the absolute value sign inside this p of x. And again, at this p of x, you could have some negative values, for example, that makes it really large, absolute value total. So if we're avoiding that and making every single thing positive, so you might actually have a less value. That's why this less than value is. symbol here, and also this k. K is just a number such that k is greater than or equal to the fourth derivative of f of x for any value in this range for x is greater than a, less than b. So again, so that's pretty much, it's going to be less than. We're just picking an over a really high number k. That's minimum value is the highest possible derivative here. Fourth derivative in this domain. So that's why it's less than equal to. So that's the absolute value. It's going to be less than this number here. Yeah, and again, this less than equal to, explained a lot of this in the other error-bound proofs for the trapezoid and midpoint rule. So now what we have to do is solve for the integral, so solving for the integral of the absolute value of p of x. We get, well, when you break this up into from a to c, and then from c to b, and these are the piecewise equation we plug in. So we're doing integrals of these. So since there's it's written into two integrals, we write it like this, but we want to get rid of the absolute value sign. So note that x minus a, so first thing, x minus cubed is, well, greater than 0 for this part right here. X is less than c, less than a, because in this case x is always greater than a, so that this is always positive. So first, that's always positive. And also note that in this case right here, and also note that at a, so what we have here, if we just look at this part right here, and then we go a minus a over 3 minus 2b over 3. What we get here, this is 3 over 3. Yeah, this part right here, if we just add these up, I'll explain what I'm doing in a bit. This is going to be 2a over 3 minus 2b. Yeah, so this equals 2, well, this is just going to be, in this case, take the 2 out, 2 over 3, a minus b. Since b is greater than a, so what this means is that this is always less than 0. So that's always less than 0, and we also know that, well, if we look at the c value here, when we plug that in, so c minus a over 3 minus 2b over 3, this equals 2, that's the c, that's just going to be, well, a plus b over 2. And then use the common denominator. We're going to have to get the 6, 2b over 3. So times by 2. This is going to be 4. Put a 2. Put a 2. This becomes 6. So again, times by 3. Put a 3. Put a 3. So what we get here equals 2. Yeah, equals 2. In this case, let's just do this 3a, that's just going to be a, 3b minus 4b, that's going to be b over 6. So again, this a, what we have right here, b is again greater than a, so what this means is this is always going to be negative. So if these are always negative from a to c when we plug those in, and if we look at it, so what we have is a positive number, x minus a, the cubed is always positive, and then this is always negative, and this is a linear function. So that means if you have something like this, x, y, so you're going to have some sort of function like this, where it's always negative. So what we'll do is basically flip this around. So flip these values around and remove this absolute value sign, so that it's always positive. Yeah, so basically what we have now is a over 3 plus 2b over 3 minus x is always greater than 0 for x is between c and a. And then let's say now if we look at b, so let's say at x equals to b, we have now in the same situation, scroll back over here. Or actually, before we get to that, let's just deal with the second part now. So for the second integral, x minus b cubed, this right here, Yeah, this right here is always going to be, well, negative because we have c to b and c is less than, C is less than b. Yeah, so then this is less than 0 for x is less than equal to b, less than, yeah, I'll put equals to the sign there. Yeah, same with above here, so equals to, because if you put an a, just equals to 0. So this is c right here. So this is always less than equal to 0. So what we need to do is write negative, not negative, we just switch these around. So we'll have b minus x, and we want to again remove the absolute value sign. So write it as this, and then similarly for this function, x minus 2a divided by 3 minus b over 3. X minus 2a over 3 minus b over 3. What we get now, so when we have this function here, when we just consider it, and let's just plug in our c value. So c minus 2a over 3 minus b, this is at x equals to c. And then this equals to, again, a plus b over 2 minus 2a over 3 minus b over 3. And again, common denominator, this becomes 4. This is 2. This is 2. This is 2. This is 3. 3a, 3a. This equals 2. This is going to be negative a, 3a minus 4a. 3b minus 2b, that's just going to be plus b over 6. And again, b is greater than a, so that this is always b minus a. So this is always positive. So this is greater than 0. So we could just leave it as is. And also, yeah, so since b is greater than c, then what we have is, in this case, this has to be greater than. So b is b minus 2a, just to be complete. This is greater than c minus 2a, or that equals to this one right here. So it's greater than this b minus a over 6, and it's greater than 0. So what that means is, we could remove the absolute value signs by rearranging p of x to keep it always positive. So from integral from a to b, x minus a is always positive, but now we've switched these parts around. This has been switched, and this has remained constant for this range. So we switch around just so we can get rid of the absolute value sign. And when we switch this, we're not changing any value. All we're doing is changing, well, the sign of it. We're not changing the absolute value of it. We're just ensuring that it's always positive. And now simplifying further by using the transformation x equals a plus b minus t for the second integral, we can show that both integrals are equal. So what we do is let x equals 2 a plus b over b minus t, a plus b minus t. Then t is going to be equal to, we'll just move it over, a plus b minus x. The derivative dx, this is equals to negative dt. And at x equals to c, what we have, x equals to c, let's write this neater. At x equals to c, we have t is equal to, to a plus b minus c, and then this c is, I'll just save time, this is a plus b over 2, that's our c. And again, I will write these common denominator here, 2 over 2. And as you can see, this is just subtract the same thing. So this just equals to a plus b over 2, which equals to c. So we haven't actually changed that value. So now at x equals to b, that's this part here, we get t is equal to a plus b minus b, which equals to a. So the last part we need to consider is, the last two parts is this b minus x and this x minus 2a over 3 minus b3. So x, or actually b minus x, so b minus x equals 2. This is going to be b minus this part right here. So b minus a minus b plus t. So these b's cancel. This equals to just t minus a. And that's what we're left with there. And then the last one is x minus, scroll here, 2a over 3 minus b over 3. This equals 2, plug in our x value, which is our new transformation, a plus b minus t minus 2a over 3. So this is 2a over 3 minus b over 3, because this is our x value, and then minus that. So now again, common denominator for this 2a, that's 3, 3, the b is 3, 3, this equals 2. This is just going to be 3a minus 2a, that's just a over 3. This 3b over 3b minus b, that's just going to be 2b over 3, and minus t. So what we have is now integral from, actually, yeah, I just already wrote it down here. Yeah, and basically, thus we have this integral of this absolute value sign. We got rid of the absolute value sign for the first one here. We just switched these around. So this is from integral from a to c x minus a cubed, etc. And then when we plug all of this transformation in, we have this negative. Yeah, this negative, and again, the negative comes from the derivative of this transformation. So we have a negative dt. So integral from c to a, now we have this t minus a, this is a cubed, this is 2b, this is t, and this one is actually, this is t. Yeah, whoops, delete this, that's t. So this is the exact same integral, we're just using t instead of x, so it doesn't really matter, it could be any variable. It's the same thing, except these are just flips. So notice that these integrals are identical when we integrate the second integrand from a to c rather than from c to a. This just involves changing the negative sign to positive, and thus we get, so we just flip these around and add a positive. So when we flip it around, it becomes positive. It's just saying integrate from the other way around. And if you notice my properties of integrals video, you can see that in the video link below it, you'll see that it just makes it positive, or just switch the signs. So we switch the signs and it's be exactly the same thing. So we can just add these up. So now we'll just simplify it, so it's 2 times a to c, etc. So we have this. And now we could simplify even further this integral by looking at this part right here and simplifying that. A over 3 plus 2b over 3 minus x. This equals to, first take the negative out of it, so when we have right here negative a 2b over 3, and what I'm going to do here is this negative x right here. I mean, it's going to be positive because we took out the negative out. What I'm going to do now is minus a plus a, so we're not changing anything, and you'll see why I'm doing this later. So now times common denominator top and bottom, so what we get now is equals 2 negative, and then this subtracts it out, so negative 4a, so negative a minus, plus. So negative a plus 3a, that's just going to be positive 2a minus 2b over 3 plus x minus a. And then put this minus back in. What we get now is what we get here is this flips around and take the 2 out, so 2 over 3 b minus a. So we simplified just so we can get a b minus a. Now we have an x minus a right here. So we simplified it so that we have this x minus a, and then we have all of these non-x variables in terms of, again, b minus a, which is what we all want everything to be, and you'll see that later on. Yeah, now putting this all together and then also solving, we get over here, so put that integral back into this, and now when we solve it, we multiply this out first, so integral of, this would be, well, 2 times 2, this is 4, b minus a over 3, integral from a to c of x minus a cubed, minus, now there's a 2, integral from a to c of x minus a 4 dx. And now evaluating this integral, we get, this is 4 over 3, b minus a, this is going to be now x minus a, take the 4 divided by 4, this is from a to c, And then same thing. Yeah, same thing here. We get now, this is going to be x minus a 5 divided by 5. This is from A to C. And then when you plug in these values, when you evaluate it, we get this. Well, we could also cancel these out. I'll just put this, I'll keep it there for now. B minus A, this is going to be, plug the C in, C minus A, 4 over 4. When we put in the A's just cancel, so we can just ignore that. So 2 over 5, now we have this C minus A power 5. And now these 4's cancel, and also note that C minus A, that equals to, well, the average, C is this average, A plus B divided by 2 minus A, common denominator, 2 over 2. I'll just write this a bit neater, so A, this is 2, divided by 2, this equals 2, this is going to be B, and then there's going to be A minus A over 2. So that's what that C minus A equals to. So putting this back down, this equals to, this is going to be A, this is to the power of 5. Yeah, so B minus A, this is going to be like that. So what we have is a B minus A, this is 1 over 3, times it by B minus A. This is to the power of 4, and then also take this, there's a 2 there, so 2 to the power of 4. Minus 2 over 5, and then what we have right here is the same thing. This is going to be B minus A, 5, and then there's a 2 to the power of 5. 2 to the power of 5, like that, write it a bit better. So we have that right there. This equals 2, putting these together. You're putting these together, simplifying further, this 2 cancels, this would be a 4. And now what we're left with, this is going to be B minus A 5. This is B minus A times B minus A to the power of 4. Those combine, and now this again, this is going to be 3. And then this is going to be, well, 2 to 4. Note, I'll just write the note, 2 times, put it over here, 2 to the 4 equals to 2 times 2 times 2 times 2. This is equal to 4. Then again, that's an 8, and again, that's 16. So that equals to 16. So what we have over here is equal to 3 times 16 minus B minus A 5 over 5 times 16. And now times by the common denominator, all we need to do is add another 3 and add another 5 here. This equals 2, B minus A 5, and factor that out. This just becomes 5 minus 3. Over here, this is going to be 3 times 16 times 5, which again, this equals 2, B minus A 5. This is a 2 here. 3 times 16 times 5. This simplifies to an 8. This cancels. So what we have right here, 3 times 8 is, and again, just doing more algebra math, B minus A. You can do this in your head or in a calculator. I just want to keep writing it out. 3 times 5 is 15 times 8. And then here, this last part, this part right here, this is just, we could write it as 10 plus 5, just want to do it in my head, times by 8. This equals to 80 plus 40 equals 120. So then this becomes, so altogether this is, altogether what we just solved is the integral from A to B of the absolute value of P of x dx equals to B minus A 5 over 120. Yeah, so thus what we have is the Simpson's rule error, or the Simpson's rule approximation error for each pair of intervals is going to be, well, absolute value of, this is the absolute value error of f, so the function f, so the error, Simpson's rule, f, absolute value is less than equal to k over 24, like I had before, and our P of x the integral of a to b of p of x is going to be b minus a 5 divided times by 120. And again, this equals 2 if we plug into a calculator, or just multiply this out. I'll just do this right here. So 24 times 20. Let's write it like this. So 24, 120. This is 0. 2 is 8. This is 4. Just do long division. And then we have this part right here, 0. And then put another 0. And then 1 times 1 is 4. 1 times 2 is 2. 0. This is 8. Add these all up. And then this is 8. This is 2. So this equals 2. Yeah, so it's less than equal to this, which equals to k over 2880 b minus a 5. I'll circle that. And again, where our k value is greater than or equal to the fourth derivative of x for the domain of x is less than or equal to b, greater than or equal to a. And now we could finally do the composite rule, and I'll explain what that is soon. So now that we have the error basically for each, if we have a subinterval of just two intervals, I mean a pair of subintervals, that's the error. So now for the composite rule, we take n as even and divide a and b into n divided by 2 equal subintervals. And the reason we do it like this is because, well, Simpson's rule is applied every 2 intervals. So we have to do we have to do n divided by 2. So for example, in this case here, if you had something like this function, and then this was from, let's say, you have intervals like this all the way here, and this is n intervals, but the thing is we're dealing with every 2. So every 2, so that these total number are n over 2. So that's what we have over there. I'll just delete this. So that's why we have it n over 2 equal subintervals, and now we have to apply Simpson's rule on each subinterval x2i minus 2 up to x2i for I is less than equal to n over 2 and greater than equal to 1. So that's what I mean. We have n divided by 2 subintervals, and note that the composite rule is simply the summation of intervals that we are dealing with, in which the number of subintervals is even. So yeah, I'll just write subintervals in there instead of intervals. It doesn't matter too much. So what we're going to do is look at a subinterval. So it's the same thing as before, what we had where we went from a to b, but now we're not going from a to b. We are going from x to I minus 2. And now the center point's not c, it's just x to I minus 1. And then this point right here is x to I. And again, this is our function f of x. And our Simpson's rule approximation is something like, it's a parabola, so let's just go like that, something like that. And this is our s, we'll call it si, so at this subinterval. So it's a pair of subintervals, so that's what we have. Where again, recall that the delta x is just simply is one of these, and then the total is 2 delta x. And where delta x is equal to the total b minus a divided by n total subintervals. Yeah, so now the Simpson's rule approximation for each subinterval or pair of subintervals is going to be x to I minus 2 up to x to I f of x dx, and roughly equals to, well, delta x over 3. So we're just writing the Simpson's rule approximation, f of x to I minus 2 plus 4x to I minus 1 plus 4x to I, etc. So that's for one interval, but now we summing up for n divided by 2 total subintervals, we get an approximation for the area from x equals a to x equals b, and that's just going to be this right here. So we're summing it up. And this is, we're just plugging, we're just summing that up, and then take it out. We have this b over a divided by 3n. Yeah, so we have that over here, and then this is integral, the summation of of this approximation here. So it's roughly equal to the summation of the Simpson's rule approximation SI right there. So yeah, in fact, to be complete, this is actually the other way around. So this integral is roughly equal to this. So this is the other way around. So this integral is roughly equal to Simpson's rule approximation. So we throw this back in here. So now we're summing that up, n divided by 2 times, and then we could simplify it further by taking out one of these terms. And exactly, if you watch my Simpson's rule video, you'll see how we have this 4-2, and here this is -1. So that we're taking out a pair of subintervals. So we're taking out 2, and in this case we're taking out this this endpoint over here, and now we are all we did over in this case, take this out and put it here. Yeah, I'm not going to dwell too much into how we get to this, but you could basically, if you were to actually start over here, f of, let's say we had f of a plus, then we have 4 f of x, let's say 1, plus, then you have f of x 2, and then we have to start over again. So then we have to go f of x 2, and then you have plus f of x 3, this is the 4, etc. This is going to be now f of x 4 plus, etc. And that's where we have this this 2 right here. And that's how we get this 2, 4. So these combined to 2. So anyways, I'm just going to remove these to not to get too messy. So just make sure to watch my Simpson's rule approximation proof, and you'll see how this occurs. So we have this always 4, 2. And that's why we have this n minus 1 right here. I mean n over 2 minus 1. Yeah, actually here I've just put an example here of what I mean, just for completeness sake. And this is what I went over in my earlier video as well in Simpson's rule approximation, just to illustrate why there's this n over 2 minus 1 right there. So if we have, let's say, approximated 3 pairs of subintervals, so we have, in this case, f of x0, then plus 4x1 plus f of x2, then we have plus f of x2, then 4 f of x3, then f of x4, etc. We have here, in this case right here, we have, this is x0, this is x1, this is x2, so this is the first pair, that's this one right here, and then we do the same thing. So there's always this x2 there again. x3, x4, x5, and then last one x6. And our x6 equals to our b, and this x0 is equal to our a. And this last pair right here. So what we have here, these add up. This becomes here f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus 2 f of x4, and then we have plus 4 f of x5, and then plus f of x6 right here. So as you can see, there is 1 here, 2 here, 3 here. And now here there is 1, there is 2. So as you can see, there is 3 pairs of subintervals. And there is, for this 4, there is 1, 2, 3. So that is our n over 2. This is our n over 2, which is n is 6. So that's why we have this n over 2, and then this n over 2 minus 1, there is a 2, and there's a 2. That's it. So we have this n over 2 minus 1, so which is 3 minus 1 equals 2, etc. And then there's this b, that's our x6, and that's our xa, and that's our x0. And you could consider it as basically we're removing one of these and putting these to the sides, etc. So now anyways, moving away from the approximation there and looking at the error, for the composite error we first have to recall the p of x lowercase that we defined earlier for just one pair of subintervals. So that's just this one. Now we define a similar function, capital P of x right here. So instead of a, we have to deal with x2i minus 2. Instead of b, we have x2i, a, and so basically that's all we've switched. And now instead of c, we go x2i minus 1. Now the error is similar to dealing with just one pair of subintervals, or one subinterval, but we have to sum it up to n over 2 times to get the total error. And yeah, so we have to sum it up with this pair of subintervals. So now this error now is going to be, we're dealing with now, this is the 1 over 24 integral of a to b of fourth derivative f of x times p of x dx, and now we're going to be dealing with this summing this all up, these pair of subintervals here. And also similar to the case with just one interval or one pair of subintervals, the following integrals are identical. So basically the integral from this is exactly the same thing we had above. So we had the identical integrals of the p of x. So 2i, yeah, minus 1, there's an error there. So this 2i, so these are exactly the same whenever we do from, remember before we had a to c and c to b. Thus the error can be simplified again. Instead of this 24, we times it by 2. So this is just 2 over 24. So that's why we have this 12 there. So now, do just as in the case for the one interval, we can rearrange p of x to always be positive and thus remove the absolute value signs as I did here. So this is exactly the same thing as when you scroll above here, except I just switched these back and forth just so that it's always positive, because those were always negative. So I just put a negative sign, just flip these around. So now what we're going to do is just simplify this further, let t equals to x minus x2i minus 2. Yeah, just so that this becomes, well, just t. And also what we have is x equals to t plus x2i minus 2. Just move this over. The derivative dt equals to dx. And now at x equals to this point 2i minus 2, we have t equaling 2. That's just going to be, well, 2i minus 2 minus x 2i minus 2 equals to 0. And now at x equals to 2i minus 1, we have t equals to x 2i minus 1. That's the midpoint minus the left point. That's just going to be, well, that's just the delta x. That's just the distance of the subinterval. So that's just delta x. And now we can just plug that in here. So this integral, we'll just deal with that first. So we have 0 up to delta x. That's this whole integral equals 2. And now we put the t in there. So there's this t cubed that's replaced. And now what we have is this x2i minus 2 over 3 plus 2x 2i over 3 minus, now the x is going to be minus t, and then minus x 2i minus 2, and then use a common denominator. So do that 3 over 3 dx, or dt actually. So we have all of this. This equals 2 now, minusing this 2i minus 2 from this. So that's just going to be integral delta x t cubed. So now we have this over there. So we get this 2x 2i minus, this is going to be negative 2. Yeah, so that's going to be minus, when we subtract these two, ti minus 2 all over 3, and then there's a minus t dt. Simplifying further, taking this out, we get the 0 delta x. Take this 2 out, we get t cubed over 2 over 3, and now we have this x2i minus x 2i minus 2. This is just, well, this is 2 times delta x. That's just distance across from the left endpoint to the right endpoint. So that's just going to be 2 times delta x minus t dt right here. And then this equals 2. Take that out. 0 delta x t3. It's going to be now 4 over 3 delta x minus t dt. So now we could just expand this out. 0 delta x. This is going to be now, so I'll take this out of here. 4 over 3 delta x integral from 0 to delta x t3 minus, and this is going to be minus now, multiply that in, 0 delta x t4 dt. So now we could just evaluate this integral. So this over 3 delta x, this is going to be t4 over 4. This is from 0 to delta x. Again, this 4 can cancel this 4. Minus, this is going to be t5. Let's write it like that. Over 5. This is from 0 to delta x. This equals to, now plug in the delta x, and then zeros just cancel. So we're just going to be left with delta x. And there's a delta x right here, so there's delta x to the 5 minus delta x to the 5 over 5. And now the times by common denominator, so times by 3, times by 3, times by 5, times by 5. This equals to now, and factor out the delta x to the power of 5. We get 5 over 3 over 15. This is just 2. I'll just put that in, how to simplify it quicker. So 2 delta x power of 5 like that. So that is what our integral of the p of x is. So now what we have to do is plug that into the, now we have to just sum it up and times by k divided by 12. So what we finally get is we have the absolute value of s, this is n, of f is less than equal to k over 12 times it by, times it by the summation up to n over 2, oops, n over 2 from I equals 1 of, now we have this 2 delta x over 15 power of 5. And now what we get here, this is just summation, this is the constant, so this equals to k over 12. And then this is just going to be, well, multiplied times it by n over 2. That's just a basic summation times it by the number of times. So we're just multiplying this constant by the number of summations, which is n over 2 over number of intervals. And then we just do times delta x over 5 or 15. This cancels. And now what we're left with equals to k over 12 times 15 is equal to, well, let's just go here, 12 times by 10 plus 5 equals to, this is 120 plus 12 times 5, that is, well, 6 times 5 is 30, so 60 equals to 180. So that's just my in my head calculation. So we have 180 and delta x over 5. And now our delta x, remember, that just equals to b minus a, this distance of each subinterval divided by n. So what we get now is that the error is going to be equal to, equals to, well, it's less than equal to k over 180, and now this is going to be our b minus a to power of 5, n to power of 5, but there's an n right there, so n to the power of 4, and again, where our k is greater than equal to the fourth derivative, absolute value of the fourth derivative of fx for x is less than equal to b, greater than equal to a. So there it is. We finally got it. It took a long time, but there's the proof for this Simpson's rule error bound. And now you know why you don't have it in your textbook or any other calculus textbook, or even anywhere online. I didn't see anywhere that showed this full complete proof. There's a lot of incomplete proofs. You have to fill in the blanks in yourself. And I just wanted to finish it all. I knew it was going to take a long time. And it did take me a long time. But anyways, hopefully you went through this. And like always, you can download these exact notes in the link below. And thanks for watching. And stay tuned for another math easy solution. Let me just scroll all the way up. Holy cow, even just scrolling up manually takes forever. Anyways, stay tuned. Have a good one, guys. See ya.